Hello, welcome back to Cracking the Cryptic, where today I'm going to take a look at the Diabolical Sudoku from the Daily Telegraph. Appears every week on Fridays. It's normally a vicious challenge, so without further ado, let's start looking at it. And as usual, in any 3x3 box, where a number can only go in exactly two positions in a 3x3 box, I'll make little pencil marks to indicate that. So you can see this 2 here combines with this 2 here to force 2 into one of two positions in this 3x3 block, and that's what these pencil marks are intended to represent. So without further ado, let's carry on having a look. We can see that we can place some pencil marks here and here with 3s. Can't yet do anything with 1s in this block, annoyingly. Some awkward pencil mark 9s up there, 4s here, 7s here, and there we can find our first big number. If we look at the interaction of 4s on this block here, you can see there's only one position a 4 can go, and that's there, so let's put that in. On these difficult puzzles, I probably would check row 8 now, just to see whether there's anything interesting going on. You can see we've got to place 2, 3, 5 and 8 in row 8. We have a 3 here, so forces the 3 over into one of those two positions. Other than that, I'm not seeing anything terribly clever. You can see we can place a big 9 into this position. Let's put that in. Now we need to work hard on this part of the grid. We can place a 5. We've got 2, 7 and 8 to place. We can place a 2 now. Pencil mark 7s and 8s in there. And in fact, that resolves the 7 here, resolves which way round the 7 and 8 goes. You can see now this has to be a 2-3 pair. So let's note that in. And again, we now need to work hard on this block to see what these restrictions might mean. You can see we can place 6s down here. Anything else obvious? 7s forced into the top row, but we don't have any 7s in these two blocks to help us with pencil marks there. In fact, I've just spotted that's a big 7 in that position, so maybe that will allow us to find a way into the 7s over on the right hand side of the grid. Not quite yet. 2 8s. It's an 8. If we look at the 8s here and here, and this 8, we're able to get a double on 4 and 8 in this block, and that will certainly attract my attention now. That's going to give us a useful pair of 9s there, which interact with this 9 to give us more pencil mark 9s down there. Now, anything else? 5s, yes, 5s we can pencil mark now into these two squares, which in fact we can go further than that. Let me just remove those 5s. If we look at the way 5s interact on this block, we have a 5 here and a 5 here and a 5 here. And once we've got this 4-8 double, i.e. the 5 cannot be in this position, the 5 is forced down into this square. And the moment, this is one of the useful things about this notation, is the moment I write a 5 in this square, I can write a 9 in this square, because I know that the 9 can only go in one of these two positions. So once one of these positions is ruled out, the other position must be the right one. So let's put the 5s in, pencil mark 5s over this side of the grid. Now place the 9, and that allows us, in fact, you can see I'm going to be able to do the same thing down here with the 9s and the 2s. I can place a 9 now here, which gives me a 2. And now what I must do is remember to use these pencil marks as fully as I can. You can see I can now place a 2 here, the interaction of the various 2s around the grid. 2, 2, and 2 here. And that 2 here resolves this 2-3 double down here, like that. Okay. the interaction of 3's on this top 3 by 3 block is now useful. This 3 here rules a 3 out from this cell, this 3 rules it out from this and this. So I am able to pencil mark 3's in like that, which gives me these two 3's here. And this 3 now also allows me to pencil mark 3's there and there, like so. This block now, these extreme positions can only take 1 and 6, and we have 6 here. So we can now write this 6 in and write a 1 in. And that allows us to pencil mark 1's down into these two squares. And that allows us to pencil mark 1's down there too. 1 is forced into one of those two positions. Just making use there of this 4-8 double and this 1. Okay. Actually, so far it feels like we've made relatively smooth progress. 3, 8, and 9 down here. 9, 9, we can pencil mark 9's in. And there's a nice bit of logic. And this is another reason for using these pencil marks. We need to look at the interaction now of the 9's we have here in row 4 and 6, and these 9's that we have here in 4 and 6. And we now know this is called an X-wing pattern, and what we can deduce from this is something very important about this block here. In fact, you have a 9 here and a 9 here, so technically the 9's could be pencil marked like that in this 3 by 3 block, but we're actually able to rule out this 9 using this X-wing. How do we do that? Well, let's imagine this cell was a 9. If this cell is a 9, we know that this cell will be a 9, because we know the 9 can only be in one of these two positions. So we know that if this is a 9, this cell will be a 9, and vice versa. If this is a 9, this cell will be a 9, by exactly the same logic. So whichever way round these 9's turn out to be in the final solution, there won't be any other 9's in rows 4 and row 6. Now that therefore means that this cell cannot be a 9. If you don't believe me, let's try it out. If this is a 9, this would have to be a 9, and this would have to be a 9, because this couldn't be a 9. So we'd end up with repeated 9's. So we can remove this 9 as a possibility and place the 9 here. So that's the first bit of, I suppose, more advanced logic we've had to find thus far. Pencil mark. Oh, that's quite interesting actually. Yeah, we can pencil mark 4's into these two positions. Now, this block here, that 4 can only go now in this cell. It can't go in any of these cells, can't go here because of these two 4's, and can't go here or here because of the 4's in the columns. So this is a 4, and that's got me, I'm just having a look now. Up here, there's a uniqueness point, I think, that we might be able to use relating to the 4 and the 8's. So what I'm looking at here is the relationship between this 4-8 pair that we have in this 3 by 3 block, and these two 4's here, and the necessity to place 8's somewhere in this 3 by 3 block. I'm just going to remove this 3 here just for the sake of exposition initially, and ask ourselves, you can see we have an 8 here, so the 8's are forced over into these 4 squares somehow. Now I want to ask whether this would be a possible arrangement. Is it possible that the only place an 8 can go in this block is these two positions? Now it should be clear, hopefully to everybody, that this is impossible, because we know that this is a good Sudoku puzzle and it has only one solution. Now, if we discovered that this was the case, this arrangement of 4-8's was the case, then we actually got two solutions to the puzzle, because there is no way of validating which way round the 4-8's go, because if this is a 4, this will be a 4, and the 8's will be here and here. but it's just as valid for this to be a 4, and this to be a 4, and the 8s go here and here. So we know this arrangement will be impossible. Okay, so I'm just going to remove the 8s again, put that 3 back. So I know that somehow I need to avoid that possibility. Now let's look at that now and think about what that might mean. So I'm thinking now about what are the actual possibilities along the middle row of the grid, because I suspect we'll be able to find something interesting. So I'm going to diverge from my notation slightly while I put in the options. So you can see this has got to be 3, 4 or 8. This cell here is going to be 1, 3, 4, 6, 8. 3, 4, 6 and 8. 1, 3, 5, 6. So that's interesting. That's very restricted, that square. This square here, 1, 7, 8. Is that all? So this is just a 7, 8. That's again very interesting. It's very restricted. And then 1, 2, 3, 4, 5, 6, 7, 8 here. Okay, so this is the arrangement along this middle row. Now I'm fairly sure if we study this and we remember that we need to avoid this being a 4-8 pair, we'll be able to deduce something interesting. So let's have a think about this now. So you can see immediately if we're going to avoid a 4-8 pair here, then either this cell or this cell are going to have to contain a different number to a 4 and an 8. Now there are only two options here, a 3 and a 6. So either this cell or both of them will contain a 3 and a 6. But that's very difficult now because we have this square here which can only be a 3 or a 6. So given that we know one of these cells at least will have to be a 3 or a 6, the other 3, 6 will have to be in this square here. So it's not possible for this to be a 6 and this to be a 3. We can immediately rule out that, but we know that there will be a 3-6 pair as a combination of these two cells and this cell. Now what does that mean? Well, that means this cell definitely can't contain a 6. If this contains a 6, this will contain a 3, these two cells will be 4, 8, and that will give us our uniqueness problem. So we are able to remove this 6 as a possibility. Now that's brilliant as well, because now we have a 7-8 pair along the central row of the grid. So I'm able to actually eliminate the 8s from these two squares here, and in fact pencil mark 8s into those two squares. Just wondering whether that's going to give me anything immediately helpful. And these 8s here, that allows us to place penciled 8s here. And now we actually have an arrangement of 8s in this block and this block that are similar to the ones that we studied last week when doing the diabolical, in the sense that it's not an X-wing, but it has sort of X-wing properties in the sense that we know if this cell is an 8, then this will be an 8. And if this is not an 8, this is an 8, and this will be an 8. So if I was of Mark's disposition now and keen on bifurcation, this is definitely where I would be looking. I'd probably guess this was an 8, because I know that if this is an 8, this must also be an 8, and you can see immediately, I think that's going to give us an 8 here and an 8 here. So it's going to give us a variety of 8s plotted around the grid. So that would be one way to proceed, but that's probably a little bit too far down the bifurcation route for my liking. So I'm going to stare at this a bit longer and see if I can see anything cleverer. One of the things that we might think about doing here is, because we've got this 7-8 double we've discovered along the central row of the grid. Often with these puzzles you can find chains along lines like this. Just by examining the rows and the columns that are contained within these sort of hidden doubles that you've found. So one of the things I would want to look at here is whether there are any cells in the rows and columns containing this 7-8 pair that contain double. So, I mean, for example, if we look at this square here, this square can be a 1, 2, or an 8. Well, it can't be an 8 because we've locked the 8 into this. So, sorry, 1, 7, or 8. Can't be an 8 because of these 8s here. So this is a 1, 7 double. I'm going to just divert from my notation just to illustrate this point here. Now, again, this cell here, this is a 1, 8 double. So it's interesting how many doubles we're finding already down this line. Let's do the same thing over here and just see if we can find out, see if there's any more. So here we've got 3, 6, 7. So this is a double as well. And 1, 6, 8. Okay, so you can see, and the reason for doing this is that I'm wondering whether by picking one end of the chain of doubles that we've found, whether we can force something. So I'm looking at this cell in particular, because everything, you can see if we pick this to be 7, a whole load of things flow. If this is a 6, the effect of that is useful in that it locks a 6 in here. If this is a 7, this will be an 8, this will be a 7, this will be a 1, this will have to be an 8, and now this square has to be a 6 again because we have this one pair here. So either this is a 6 or this is a 6. Therefore, this cannot be a 6. Wow, there you go. So it was useful to do that. Won't always be useful, but I often am suspicious with these harder puzzles where you discover something like this. It's probably not by accident, and we have to make the maximum use of discovered doubles like this, and that was a way of doing it. So we've discovered that whether or not this is a 6, this cell is forced not to be a 6. Therefore, where can we place a 6 in the bottom row? Only here. So let's put that in. 6. It's probably not going to be of any use at all, but let's see. We can now pencil mark 6s here. I've got to be a bit careful now because I'm mixing up my notation here, which I never like doing, but okay. You probably now want to repeat the trick again because you can. Again, this is suspicious to me. It should be to you too. You can see that by picking a 5 here, we're affecting some cells down the column 9 of the grid. By picking a 6 here, you're running into a chain again because this 6 affects this this cell. It forces this cell to be a 7. It forces loads of things in this box. It forces this to be an 8. I'm wondering about the rest of this box now. If we focus on these cells across, we've got 3, 5, 6, 7, and 8 to place. And you can see we already have 3s over here, and we have a 7 here. So that leaves 5, 6, and 8 to place. And so that these two cells are 5, 6, and 8. But if we rule out 8 here, we'd have a 5, 6 double. So whether we pick this to be a 5 or this to be a 6, these two cells can never contain 5s. Because if this is a 5, obviously these can't be 5s. If this is a 6, this will be a 5, 6 pairing, and again we'll rule out 5. So there is no 5 in either of these positions. So I'm not certain that's going to be helpful, but let's stare at the grid and think about whether it might be. No 5 here. Yes, there's now a 5 in row 4, can only go here. So let's put that in. That might be useful, maybe. We can put little 5s in here, just based off the logic that we just did. And in fact, aren't we done now? Because can't we just use that same chain to force a contradiction here. Let's just check that. So you can see that in this cell, the valid options I think are only 5 and 8 now. 1, 2, 3's ruled out, 4's ruled out, 5's okay, 6 is ruled out, 7's ruled out, 8, yes. So we have a 5-8 double here. Now again, let's go through this lot. It's the same chain as before in effect, but this time operating on this cell. So if this is a 5, clearly this cell is a 1. If this cell is not a 5, this is a 6, 7, 8, 5. So either way round, you're going to have a 5 pointing at this cell. Therefore this cell cannot contain a 5. Now once this cell cannot contain a 5, it must contain a 1, because it's the only other valid option for this cell, which means this is a 3, this is a 1 here, and you can see I think now that we're home and hosed in terms of the solve. There's not going to be I don't think there'll be any hold-ups from this point forward. It's simply a matter of filling in the grid. So very interesting puzzle as usual with these hard diabolical puzzles. They really do take a bit of thought, but this time we were able to use chaining and intuition a little bit to crack it open. And I hope you've got something from watching the solve, and we'll see you again next time on Cracking the Cryptic.